Okay, so welcome everyone to the lecture. And I'm a bit confused that the majority of you obviously is online. So that's not your fault because you are here, that's good. But of course, yeah, so let's observe that. And if this continues like that, then we should think about doing it completely online or stopping the online transmission so that everyone comes here. But anyway, please remind that being online is not intended as a full-time replacement, but it's more like a backup. Not so I will not guarantee that you will get the same experience as if you are here. Okay, so welcome. Last time we started to work on analysis of sentences using the stanza library. So trying to get out some information about text from using this stanza, which actually is able to annotate words with some information like base form and grammatical function in the sentence, relation to other tokens or words in the sentence, and so on. This library itself is doing that using a neural network. So it's like more like an LLM. It's trained with a lot of data. But our analysis that is kind of on top of that now, of course, is rule-based, or we just use the information. So this is one possibility to extract this information. So let's a little bit play with that further before we then, during the course, move on to more sophisticated techniques. Okay, so let's let's start with let's continue with what we started last time. So last time we started with the subject of the sentence, and we managed to get our program in a shape that it actually detects always the subject. And we also were able to solve this issue that in this case is here, the subject is a combined word consisting of two words, Miss and Piggy, which are related. So we solved that. And we solved that by using the relations between the words that we get from stanza, where we have like that one here, the proposition. Yeah? So if we have proposition and it's related to our token, we can combine these. So let's see what the next step is. The next step now is we should maybe detect the verb. So now we have the subject. Now let's look for the verb. So we can reduce the sentence to our, let's say, to the base information, which is subject, object, verb, or subject, verb, object. At least for most languages, So if we get this out, we should be able to have some information in a kind of about a sentence or the content in a kind of a, let's say, standardized way. So we always know what is. With this information, you can already do some analysis if you want. You could. I mean, of course, you can do other analysis as well, but this might be one approach to reduce the sentence to, let's say, the core information. Okay, so let's find the verb. If we comment in our print again, we could be able to see how the verb would be detected, because we need to get the information. So let's comment that in again, this print command. So we see the output. Okay, so let's look what verb would look like here in this structure. Here we have a noun. we have here we have an object. Home. So that would be the object. The deprel is object, and upos is noun. Let's look for a verb. Here, get, for example, the verb. So this is type verb, and actually is the root of the sentence, or the action. Verb. So maybe let's look for the tokens that have the verb, and then of course we have the problem with the auxiliary verbs. So we have some here. Do auxiliary verb, which is related to that. So the same thing as with the propositions. We now need to look for the auxiliary verbs again. So let's see. Let's try if we can do that. It's probably quite similar logic as we have it here. So we can maybe copy that. So if the deprel is the root, which is the verb of the sentence, and when we look for where the head is a token and it's the upos is aux. Let's change that. Let's say this is root. And in this case, maybe let's check for the upos as well. Or maybe not, because the root could be a. Let's see what happens. Might be not. So let's put the verb afterwards because it's do get. And then print. Let's try. If this runs. Okay, it doesn't look so bad. For the first sentence, we have the only thing that I'm confused of is because why the I is double. Because I would call is fine. I give in sentence 3, we are lacking the subject. Okay, there it's didn't recognize, but this may be a special case. Okay, but in general, it looks not so bad. It does not handle the wouldn't correct. The not is not really handled correctly. Yeah.
Given call, give, recognize, happen, get, and get. Six, it would be verbs, like. Right?
6 verbs?
Yeah.
Okay, so we have call,
Yeah.
give, recognize,
happen,
get, and then one more get. Yes. Yeah, it's fine.
So in previous code, if we change only other dot llama and subject, we only change root, then we are getting this result.
Yeah. Okay. So what did you change?
Only I changed this proton dot lemma and just root, nothing else.
Lemma and so in which line? In here?
Yeah, the verb is equal to proton dot lemma.
Here?
Yeah.
And you changed it to verb, the order.
Yeah.
So you said verb.
Yeah, the verb.
Like that?
Yes.
Okay. What happens now? Yeah, but now you have this strange thing. Happen could. No, the other order was better, I think, because it gives you more than the more correct order. No, the issue now is that it definitely does not handle the negation correctly. So it's not, it's would, not wouldn't, and didn't. That's the end, but the apostrophe T is not correctly handled. Probably because it's not recognized as one word. Let's see what happens or what actually is done with that. So maybe we need to do some pre-processing here. It's here. Hello. Okay. Where is it? I punctuation. Okay, we are not. It's not printing everything here. We have the problem that we do not see everything now. I do get right. I cannot scroll more. The buffer is just too small. I don't see things above. So now let's try the object first, because that's easier, I think. Let's look for the object. The logic is the same. So we look for the object, and then we look for the proposition, because it's a subject and a noun again. Yeah. That's a simple thing here. And I think it should be the same. So let's see. Yeah.
Did it has a space in between, but there is not an apostrophe in the text. I'm checking that on slide.
Okay.
Could we check there is a connection? It should be didn't or
Yeah, it should be didn't. So I think the problem is here really that we would have to replace it in the original text. Let's see. It's like that one, right?
yes.
So what we could do is replace that with not. That's actually what it is. Yeah. So we could do a string replace first on the doc before we do it. So we get really a not. Yeah. And then we could, let's say doc is equal to doc. I think it's replace, I hope. Yeah. Replace, just try. So replace this one with space and not. So that's the actual thing we want to do. And in that case, I think it should, before it puts it in the sentence, so it should replace that with a, say, correct. Let's see if it works. No. Document object has no, it's a document. Sorry, it's the original text that we need. Doc is bad. So we need to do it different. We have to use the text first. So let's cut out the text. Let's do it like that. Okay, so it's so it's our, let's say, text. And this is now changed. I wanted to do it with the text, not with the text. So let's replace so this is our input here. This is now the replace text, and now we can do it like that. So basically I just cut out the text, moved it to a separate string variable, now do the replace, and hopefully that.
Now we would not without the space in between. Okay.
So it does not change anything because obviously it does not, we do not include the not correctly so far. Yeah. Right. Let's see. Let's print the not here. To avoid that we get too much output, let's just do say yeah, must be double equal. So if token lemma is not, then print. Ah, das ist eine Schleife. Ah, jetzt verstehe ich, warum das nicht geht. Okay, und das ist. Okay, so it's now it's print. And now it's not filling up the. So. Yeah. Keep out of the loop.
The text itself doesn't have the apostrophe T.
Sorry? Yeah.
There is a space without an apostrophe and T.
So it kills the not, or?
If you check the text, it's there is in here.
If I do print here?
Yes.
Print. Okay, let's check if that's correct. Print text. Yeah, so that's maybe better. Here for a moment. Maybe it's an escape issue that this apostrophe is not handled correctly. Yeah. Well, I would not. Ah, there's a strange character. It replaces the not really candidate.
Then we replace it as
It's off premises. So
okay, that's inside. Yeah. Okay.
yes.
Okay. The error is here. It was. Yeah. It would not call. You know, it's there. That's the mistake. Okay.
And third line, optional security didn't.
Yeah.
The apostrophe is missing there. Didn't recognize her.
Yeah, you're right. It's not there because it's for whatever reason it was not in the original text.
Yes.
Okay, so let's yeah, so we could of course do that as well and handle this case also. Ah, okay. Okay, now it changed that as well, which was not intended because it's then in. Okay. That's not good. That's too That's too smart. No. Because it kills other things. Okay, how can we? Let's do it like that. Okay, this is not perfect, but we would summarize that under pre-processing. And why does not replace that? Because they're not changed. Mistake. Right. Okay, so we tried it, and now it's hopefully better. Yeah, I do not want to end up this code. Okay. So what we see here is that sometimes we have to do some pre-processing to remove, let's say, slang stuff and abbreviations and so on. Of course, this could be made more sophisticated than just this little replacement here, but for the moment, I think it's fine. So now we should have also in the output a not. Let's see. Yeah, maybe we should switch the output on again. We can add the negation as well correctly. Sentences, and now we do.
Not seen as part of this PART.
I think we have to do that first because it's. I just want to know what the not is in. Let's search for not. Here we have it. Okay. So it's an adverbial modifier. So we have to look for these. And have to include them. So let's look for the verb. This is the verb. So we look for the auxiliary verb, and we might look for and it points to the head number 10, which is actually the verb. Yeah, that's good. So let's or oppose. What's the DEPREL? Yeah, dependency relation is verb field modifier. So adverb mod. Adverb mod, yes. Yeah, it's proposition. Yeah, right. Sorry, you're right. Perfect. So, okay, thank you. Let's try. Okay, it should be get off here in this case. And so the order is, maybe we need to do it differently. To check the order, let's double that and say, okay, if it's the U-post, it's at the end, it's in front. And if it's the, oh, let's remove that and distinguish the two cases. Because the order is, it's off get, not get off. So it's, the order is wrong for English. So let's split it. In this case, it should be probably at the end. Right. And let's comment out the massive printing here again. Okay, now we have more modifiers. So would call not really. And if just, we get some more information. It's not only the negation, which we could filter out in addition. So we could, of course, reduce it to not just saying we do not want to have the others as well. So let's just make an additional filter here and say, and lemma is equals not. So we do not get the other modifications to get it a bit more clean. Yeah. Okay, would call not. Okay, now it's I'll put it in front. Oh, then it's not would call. Okay. Yeah. It. I gave right Lady Gaga credential. Security to recognize not her. Okay, this is not perfect, but already a step forward. So we can now see for each sentence, we can extract, let's say, the core info. Now we know security do not recognize her. That's, we know I do get right home. So these are kind of the essential things from each sentence. That's the idea. Of course, this will work basically with any English text at the moment. You can change the language as well, but it should work with an English text. And right, so this was basically to show a little bit how we can deal with these things. Okay, so now we create some basic information from the text, and with this we could now implement, let's say, some rule-based processing on that. We could detect certain words or whatever, and this brings me now to the next thing that we want to briefly investigate before we move on to more deep learning related things. By the way, in the deep learning course you have in parallel, how far are you there now? Convolutional neural networks. Okay, good. That's fine, because we can, so you know what a neural network is and stuff like that. Okay, you can build on that. Good. Okay, so before we start with the deep learning techniques, we actually use them here as well because Stanza is based on that. But before we investigate it further, let me have a brief look at this. First deck. Let's add a second slide deck. Just a second. Okay, where we are? We are in. No, it's actually left. Yeah. Select slides. No, it was the language model stuff. Next one. Are we missing something here? Or what's the problem? It was already in there. Do we have it here? Okay, so what I wanted to discuss now is the first one anyway. Is a short excursion to handling logic on text, which was done in the days before we had the actual large language models. And it still is, of course, interesting because, of course, when LLMs became up, now for the moment everyone is doing LLMs, but nevertheless, questions like explainability and things like that come in more and more again. So we have to think of more about hybrid techniques. And a very early example of handling logic is the so-called Prolog language. So Prolog is an acronym. It stands for Programming in Logic, and it was designed in the 70s. It was is a programming language for programming inference on symbols. So the idea was you define rules and you define knowledge. And this is basically the basic problem of all symbolic approaches. You have to define the knowledge somehow. And if you do that by hand, then it's very tedious because you would have to formalize the knowledge, everything you know about a certain problem or domain in rules. And then you could make inference to that knowledge base in that sense that you ask questions to the knowledge base and the knowledge base answers. So it's more like querying the knowledge base. The problem with the rule-based thing is that it's absolutely exact, and that's of course on the other side also the advantage because you know what will happen. You can deduct the steps. We now have let's say another idea that is called the retrieval augmented generation, that we do a similar approach but using LLMs. So here the idea is we will have a closer look on that as well later. Here the idea now, the modern idea is you have the knowledge. For example, you have documents from your company, but now you do not formalize the knowledge, but you turn it into a word or a text embedding. What an embedding is, we will have discuss next. And then you, let's say, do querying by turning the query that someone has, which is natural text, also into an embedding, and then match the embeddings. And the embeddings, of course, are not exact because they are vectors, and you could calculate, let's say, a distance or a similarity between the vectors. So it's not an exact matching, true or false, but it's not logic in that sense, but it's kind of a similarity matching, and this makes it much more flexible. So that's an approach that in principle resembles something to these old ideas, but of course is more generic and more flexible and easier to implement because you do not have to formalize the knowledge. Yeah? However, of course, still it is inspired by the idea that it's sometimes better not to let the LLM just talk freely in space, but derive something from a given set of information that is kind of stored in an exact manner. So the early approach was to use, let's say, logic in the sense that you compare symbols. And the idea was you formulate everything you know about a domain in facts and rules. And then you could interrogate the system and let it derive new rules. So in this example, this is German, but I can guess it. So the syntax of the language is that it has facts, like, for example, a rule. This is a rule. And it says, okay, someone is the grandfather. So X is the grandfather of Y if X is the father of Z and Z is the father of Y. So you have this transient logic. It's a logical rule, yes. And now you could ask the system, now you formulate facts, so this is a fact. So you say Adam is the father of Tobias and Tobias is the father of Frank. And now you could ask the system, is Adam the grandfather of Frank? And it will be given true because it has this. So that's the idea. So rules in Prolog are expressed by this syntax, and you formulate a statement, and then you have double the. So this is like an arrow, and then you have this is the comma is the and relation. So the and of relation. These two have to be true. But these are variables. Capital letters are always variables, placeholders. And that means that the system now would, if it has a knowledge base not only of 2, wow, this is annoying. I move it here. It's a problem in the cable. So the system will find all solutions for x and y. Not only the first one or something, but it will give you a list of all possible combinations of x and y that are given in the knowledge base. And of course, the rules can be more complex. You can have more complex relations. And of course, this is a typical example to explain it. The ancestry or the relations, family relations. But of course, it can be more complex. However, as you can imagine, formulating the rules will get more complicated over time if you have more complex relations or more complex scenarios, because it's really difficult to formalize everything as a condition to that extent. But the idea that people had when they designed that was to have a system that you just write down everything and then you could ask questions, and the system will answer about a certain domain. And it will create new knowledge by deduction. So these rules are kind of deductive in that sense that you formulate, you have to do information, you deduct a new one. In this case, this is a grandfather. So this is a new information that is not manifested in the knowledge base. And yeah, it works, but it's of course it's not very powerful in that sense that it's too much effort to program more complex scenarios. Nevertheless, it has been used for certain cases, especially where you want to add logic to other techniques. For example, the IBM Watson system of 2013. So the first system that won this Jeopardy championship against the human. It actually was a hybrid system. So it combined text processing in a more classical way, like we did it, and Prolog logic with neural networks. And in these days, it was the best thing. Then, of course, the pure neural deep learning approaches succeeded more, like with ChatGPT and so on. Now we see that maybe there are also limitations or limits, that we reach the limits, and you see that, let's say, more smart approaches like DeepSeek are comparable to the, let's say, brute force approach. ChatGPT just make the model bigger and train more data.
Yes.
Then you see that there's room for improvement, also using, let's say, replacing pure computational power with intelligence, human intelligence in the design of the model. And of course, explainability is also an issue. Okay, so that's the thing why I think we should have a short look on that, because it's kind of a predecessor of modern techniques, and also still something that might be relevant in some aspects. And to do so, we can play with that. I prepared something for you, and it's in the dev container, and I hope it works. So there are different implementations of Prolog interpreters. So a Prolog system, of course, needs some kind of runtime because something has to do the actual search and support the language. And the original Prolog implementations, of course, were written in December or something, but today we have one quite frequently used is the JI prologue, which is kind of a runtime system written in Java, so you can embed it in Java applications and use it there. And I added that here. And you see that it's this program prologue runner that you should have in your package. Is that true? It's in the, now it's not on the top level because it's in a package. It's in a Maven project. It's in a main Java DEH and it basically uses this library. So you can imagine that it's a Java file. It's implemented in Java, and you can use it in your Java program to execute prologue. Yeah. And the basic structure here is now that you have, you have the JIP engine. This is GI prologue, and it's actually created. It's a class, and you create an object of it, and you can print out the version and so on. And then you actually, I create an instance of my class here, the prologue runner. And prologue runner, my class here, this class serves as something called a listener. So every time the prologue engine finds a solution, it actually will inform the listener about it. And there are some methods on it. Yeah, so it will use this solution notified. So the prologue engine will call the solution notified method of the listener. And my class here, the prologue runner class, is actually serving as a listener or implementing this listener interface. And every time the solution is notified, it will print out the solution here. Yeah? So that's the idea. And then force it to search for the next solution. Because the problem is, if you ask the system a question, generally there are multiple solutions. Could depending on the knowledge, but in general it could be multiple solutions, and the inference engine will kind of work in parallel. Every time it finds a branch in the logic, it has to follow both branches, and this is why it's kind of done in an asynchronous manner, that all the solutions will be printed. Okay, so that's a little bit about GI prologue logic. So the usage is as follows. You create the engine, you register this listener, which is our own class here, and then we tell the system, okay, consult this file, which is actually my knowledge. In this case, so we would create a file that represents some facts, and then we could run the query on it, asking the system for some questions on this knowledge base. So the facts, this is our knowledge base. This is a list of statements that represent what we know, and then we can talk to the knowledge base. And what I want to do here in this case was to use the facts that we know from the text about Kermit and Miss Piggy, also our example, and to test this, and also to see, okay, how could we stack these technologies on top of each other or combine them. Let's create this output, this knowledge base from our text using our previous program. So the structure of such a fact is, as we have seen, is basically the predicate. So this is why it's called the predicate logic. Looks like that. This approach is called predicate logic because it has a predicate which describes the relation, and it has two or more, also one symbols that are related by this relation. So we have a predicate that refers to these things. Right? And in our case, we could, for example, say, okay, and the only thing is the Prolog syntax requires that the facts and the predicates are written with small letters, and the capital letters are kind of variables that are then looked for solutions. That's the rule. And the logic is always you have a predicate and a round bracket opens, then comes a list of the let's say nouns or symbols that are related by the predicate, and then the bracket closes and there's a dot. So that's a fact. So we could cast easily our output here of our program into this structure. Well, let's try that. We could do it if we go to our test stanza program. We just change the order. Change the order like that. No, that's not what I wanted. Okay, it depends on the original order, not on the order of the code. That's true. So let's do it differently. For each sentence, we need to do it sentence-wise. So let's define these variables here. So they are defined outside. Subject and verb. No, verb, subject, object. Okay. And then we go through the sentence. And after the sentence, we print it like that. Say it's a verb. Open the bracket. And then we say subject, comma, plus the object, plus like that. Okay, let's try. Okay, now you see it has created some predicates. So give, I, they, yeah, for example. Or here it has created do recognize security, her. Could happen it. And here you know that here you see that there's something missing. Yeah, so we should maybe leave out the comma. Because there's no object in the sentence. No? And of course, we need to make everything small letters, otherwise it will so we need to do it to lowercase. I think it's too lower. That. Okay, like that? No, too lower?
Just lower.
Lower. Yeah, thanks. We do both to make sure that it's compatible. Okay, so now we create some facts. So these are facts, and we could copy them. We could copy that to our facts prolog file, huh? And then try to run the inference on that. So let's do that. But first of all, we need to handle the situation that there's a comma here, and we have no object. If object is empty, then we have to leave it out. Else. Okay. Get Miss Piggy, do get I home, could happen it, to recognize, and so on. Okay, so now we have created some factual knowledge from this text. This is, of course, well, not very smart, but we extracted the information from the sentences, cast it in the form of a predicate. And with this, so you might now imagine you have a larger text. You could do the same with a huge text. So you could use a book, something like that, and then create the facts. So you get a lot of these statements. And now you could think about defining rules on top of that that would be more generic and help to solve. And that actually was, as far as it's documented or understandable, what they did in Watson. So they had, first of all, they had a query engine. They collected all information from the internet. And then they put it through this kind of pre-processing, put rules on that. And then afterwards, again, I think did some neural network stuff as well. So that was what's the rough logic, how it worked. 2013. So it's a bit before the actual hype, but in these days it was a really impressive function. Okay, so that is in principle possible. So now let's create this file. So what we do to have it in a way we can copy it, I would say let's remove the other prints so we do not have so many stuff in between. So comment the prints out here, and also this sentence start. If we run it, we should get the pure result. Okay, so that's our knowledge base. Now let's create this Kermit file here. Of course, we could automate that and write it to a file, but I do it by hand now because it's very simple. Call it Kermit PL for prolog and paste that in here. Let's see. And now let's try if the COBOL runner is working. So we read in this file, and then we make a question to the system. Could, for example, ask, let's ask get X. Very simple task. Let's ask get X. So we ask who gets something. So we ask for get. Now let's run the program and see what happens. Okay, we now have a lot of errors. undefined file, workspaces, NLP template. What's going wrong? Maybe the commit file is in the wrong place because it's not finding it. Yeah. Let's see where it actually deployed that. And here it is. There it is. So what's the problem? It's workspaces and a template. There. Error, permission error. Okay. Static procedure. But it's readable for everyone. So what's the problem? Consult file. Let me check if there's a problem there. It requires a different syntax. That might be that there must be the prompt in front or something. Let's see the old version. That's awesome. I think it's fine. The syntax is not the issue. Not good. Student. Yeah. Let's build that. Maybe. Okay. Let's use that, and then yeah, why not? Achso, der hat die Bericht, das ist das Problem. Jetzt los. All right, so it sounds strange why it is not building the target correctly. It's there, yeah, okay. Okay. Context undefined file. It says JIP consult file, and the file is there. So why it is not? It used to work, so that's always the answer. But anyway, I will stop it again. And do you get the same error? The same exception? Okay, so you have created this file. So that's the file. Everyone has that? Good. Nobody says no, so I assume you have it. Okay, so that's the output of our thing. And now we run the Java Prolog runner. Yeah? So we go here and then we just run it. Yeah? So that's the idea. But then I get this exception. And this exception says that it cannot open this file for some weird reason. And actually, this file is there. So at least we can see it. So if I do the normal directory ls, it's there. Yeah? So I don't know what's happening. The idea is that this program here reads in the file with the facts, and then in the next step we could ask it something. Yeah, so here we ask it. So this is kind of an embedded interpreter that you run in Java. You load it and for the moment there is some configuration issue. For some weird reason it does not open the file. So it starts. And then, I don't know why, it's not working. So I tried to rebuild the Java project with Maven. Let's do package. and is successful. So we have the jar file here. But when I run the jar file directly, it also it has another problem with the dependencies, which we can fix, but that has to be fixed. So we would have to fix the POM to create a dependency, a jar file that contains the actual Maven dependencies to make it run, which I can change. My question is more why it does not run here, because it used to work. So it's the same project. And you see that it has the right path to the file. I don't know. It's a JIP permission exception. It actually is in the main method. Then it tries to add a clause and there it crashes. I'm not sure if it's a file error or something internal. So you get the same error? Or is it someone has a success here? No, okay. Not yet, good. So modifying static procedure. I'm not sure if it's a file issue or if it's because it goes in, it says consult file, then it says consult. And it crashes assert no copy global. I'm confused actually, because as I said, it used to work like that. Anyway, I will try to solve that. That's typical configuration thing. And yeah, if I find a solution, I will let you know, or otherwise we will do it next week. The time is over anyway, so I think it's fine. But what we have seen so far, and that I think is the takeaway, the takeaway is that we generated knowledge using sensor from a text. This knowledge we have cast into the form of predicates. And now we want to run some logic on top of that. And this is a true hybrid approach because we use a neural pipeline from sensor to create the actual tokens. And now we process them symbolically. And of course, you could also then, at the end, do some inference and on the logic, and then, for example, create the output again using neural network or something. But that would be the scenario that you might use such things. Anyway, so I think we should get it run next week. So play a little bit with Prolog Runner, and then we can move on to some more deep learning based. Okay, that would be the strategy. It might be that I have to do next week's lecture only online. Yeah, only next week. But I will let you know. If you don't hear anything, everything is like always. Okay? All right, so then thanks a lot for attending, and we will meet in 1 week. Thank you. Yeah.
Ich habe das Problem mit